Good evening, everyone. Thank you for joining us for the Caltech Astronomy Stargazing Lecture. I'm Dr. Cameron Hummels. I'll be your host for tonight's event. We've got a great night, and the weather is very cooperative as well, so hopefully we'll have a lot of good stargazing after the presentation. So just a quick layout of what to expect tonight. I'll have a couple minutes of announcements, and then we'll get started with the presentation all about feeding black holes, cookies, or other things, and what happens with those black holes. And then that'll be about 30 minutes long, and then we'll have a Q&A with all of you for a couple of minutes before you have a choice to make. So we'll have a brief intermission, and we'll set up a table here in the front of the room and have a Q&A panel consisting of our presenter, Jean, myself, and two other scientists from the department who coincidentally both work on black holes. So I'll be the only non-black hole specialist up here to answer questions that you may have. You're welcome to ask questions about the content of the lecture, but also content related to, maybe something astronomy or space or physics related you read in the magazine or the newspaper recently, whatever, or some burning question that you may have about the cosmos, and we'll try and address whatever questions you may have. At the same time as our Q&A panel, as I mentioned, there will be telescopes set up outside. They're setting them up right now. And if you want to go view through the telescopes, there are some professional astronomers out there. You just go out the door that you came in and follow the signs around the building to the fields, the athletic fields directly behind us. And it's like a 2-minute walk from here. And you're free, both the Q&A panel as well as the stargazing will go on until about 9:45. So you'll be able to go back and forth if you want. If you get fed up with the telescopes and you've seen all there is to see, but you remember that you still have a question, you can come back in and ask us, or vice versa. So these events take place once a month on Friday nights. Our next one will be, goodness, I need to memorize these dates. The next one will be May 3rd, Friday, May 3rd, or May 2nd, whichever is the first Friday in May. And the presenter is going to be talking about the atmospheres around galaxies. It turns out galaxies have atmospheres just kind of like our Earth does. They're very difficult to detect, but there's some very interesting physics that pertains to the evolution and the formation of these galaxies, and he's going to talk about that. So that should be great. In addition to these events here in the department, we have kind of another series of events called Astronomy on Tap that takes place at a bar restaurant downtown in Old Town Pasadena. Even though it's a beer garden area, it's outdoors, but it is open to all ages, not just 21 and older. And it consists of two 15-minute public level science presentations on different science topics, but also live music, there's telescopes, and astronomy themed pub trivia. So it's a lot of fun. Those happen once a month on Monday nights, and our next one of those will be April 14th, a week from this coming Monday. And the two people presenting, one is from the LIGO Consortium. He's going to talk all about gravitational waves and using gravitational waves to detect merging black holes, which has been done for the last decade or so. The other person is a specialist in atmospheres of exoplanets and is going to teach us what you can learn about the formation of planets from the atmosphere around them. These are planets around other stars, very distant from our own solar system. So yeah, if you're interested, I encourage you to check that out. It should be a lot of fun. Other announcements. We just got back. We were at Death Valley last weekend for another dark sky festival that took place there. It was super fun. Getting out to national parks is great and a good way to see really dark skies because you're a long ways from the light sources in urban areas. The next one I think that we're going to help out with, there's going to be one in the Grand Canyon in June. So if you are inclined to drive or fly, the 6-hour drive to the Grand Canyon, it's pretty spectacular, and hike during the day and look through telescopes at night. It's a pretty sweet gig. So I'll put out stuff on our social media and our website when we have more information about that. And lastly, we're going to do an event. I'm in works with Pasadena City Council to try and do a stargazing event in Altadena for the victims of the Eaton fire, so that people from obviously people from Altadena can come to these events as well, but we're going to do a specific event at one of the parks in Altadena for it'll be open to everyone, but primarily for the people who were affected by the fires in Altadena. So that'll probably be in the next month or two. But again, I'll put information online when we know more about it. And just as a reminder, we're doing this live here, but it's also being live streamed via YouTube. We've got a camera set up here. So hi, YouTube audience. So if you want to check out later, we've got the recordings of all of our past 100+ events on YouTube, lectures on different topics from black holes to the Big Bang to life in the universe. And there's some really good content there, and it's all free. So if you're interested, check out our Caltech Astronomy YouTube channel. Okay, enough of my announcements. Our speaker for tonight grew up in central New Jersey and then did her undergraduate studies at Princeton in physics. While she was there, she covered a range of different topics in terms of her research, everything from particle physics, which is really hard stuff, to a variety of fields in astrophysics, including galaxy evolution, as well as work with supermassive black holes in the centers of galaxies. And then she joined the department here 5 years ago. She's a fifth-year PhD student, and here she's primarily focused on black holes and the act by which they consume their surroundings. They accrete matter, studying this observationally with a number of different telescopes across a variety of wavelengths, from the radio part of the spectrum, the infrared, the visible wavelengths, the X-ray, and so forth. And has done some really significant work in this field. And notably, she's going to defend her PhD in the next month, and she will soon be a doctor, which is quite exciting. This fall, she's going to start a postdoc in between Stanford and Berkeley. So yeah, she's really going to all the places. So it's my pleasure to introduce our speaker tonight, Jean Somalwar.
Great. Thank you all so much, and thank you, Cameron, for having me in that kind introduction. It's really great to be here. I always love when I can get a bunch of people to listen to me gab about black holes. My parents are really sick of it, and my sisters are even more sick of it. So I'm going to be telling you about what happens when you feed a black hole, or if you give a black hole a cookie. And I've completely ruined the cover page of a popular children's book. Let's see if this will work. Is it going to let me switch slides? Yeah, there we go. So this is the nice cover that I ruined. So the only thing you need to know about this book, I don't base anything in the talk on this book, except this is the reason I'm going to be putting a lot of pictures of mice eating cookies. So I hope you like rodents and some other rodents, because there's not actually a lot of pictures of mice eating cookies online. You'd be surprised. But all right, let's dive in. So before I talk about how a black hole eats, we need to start with what a black hole is. So I'll give a very basic introduction. But the definition of a black hole is a very, very dense object, really denser than anything you could imagine. It's got so much mass and such a tiny size that if you tried to launch a rocket off of its surface, it would never be able to go anywhere. It would just fall back into the black hole, even if the rocket is moving at the fastest speed possible, which is the speed of light. The surface of the black hole, or the radius where an object can't escape from, even if it's traveling at the speed of light, is called the event horizon. So to make that a little more concrete, let's go through an example and try to make the Earth a black hole. So we've got our little mouse, it's got to be a mouse, sitting on the surface of the Earth with his jetpack, and we want to make the Earth so dense that no matter how fast our mouse friend moves, he cannot escape. Even if he's moving the speed of light, he cannot escape. So for some numbers, the Earth's mass is about 10 to the 24 kilograms, or I couldn't really find a number that would make this make more sense, so we're going to go with 6 quintillion elephants, and it's about 4,000 miles in size. Right now, if you set a rocket on the edge of the Earth and tried to launch it, it would need to move about 25,000 miles per hour to escape the gravitational pull. But as long as you got your rocket up that fast, it could just go on and traveling forever. It will never come back to Earth. Light, on the other hand, moves at 1 billion miles per hour. For the Earth to become a black hole, we need this escape velocity, this 25,000 miles per hour, to grow a lot, to reach 1 billion miles per hour. Okay? So let's start shrinking down the Earth, but keep the mass the same. Okay, so we're making it a lot denser. So let's make the Earth the size of a whale, about 100 feet. In this case, if you're sitting on the edge of the Earth, you need to move 10 million miles per hour to escape the gravitational pull. We've gotten a lot faster, but we're not at 1 billion miles per hour yet. We're not quite there. So let's shrink the Earth to the size of a mouse. We're going to go with a mouse that's about 3 inches tall. In this case, if the Earth is that tiny, it's so dense that you need to move 100 million miles per hour to escape the gravitational pull. Again, this is a lot, but it's still roughly 0.1 the speed of light. It's not the speed of light. A photon can escape. So let's shrink it a bit more. Now we're going to make it a blackberry. Okay, so it's about 1 centimeter in height. If the Earth was this small, even light, even if you're moving at the speed of light, you cannot escape its gravitational pull. As fast as you try to move, you're always just going to fall back down and get sucked into the pull of the black hole. So this is a black hole. It's something that light can't escape from if you're within the event horizon. So this is a very sort of theoretical object. How could we possibly find something that's so dense that even light can't escape? We can't see it. The only reason you can see things is because photons or light is coming from them and hitting your eyes. If black holes pull in all the light, how could you possibly find them? So that's sort of what this talk is going to be about. I'm going to start with the premise that we have found them. So just accept that. Where do we find them? There's a few different places. So there's different types of black holes. I'm going to deal with sort of the smallest black holes and the biggest black holes that astronomers tend to talk about. The small black holes are formed when massive stars die. So if you take a star that's about 10 times the mass of our sun, let it live out its life, explode in a dramatic supernova. This is an image of a supernova remnant. Each color is sort of a different part of the electromagnetic spectrum. And what's left behind is a tiny little black hole about the mass of our sun. So these are called stellar mass black holes. At the center of this dramatic ball of light, there's a tiny black hole sitting there. We can see these through a couple different mechanisms. One is these tiny black holes can eat stars. So this is an artist rendition. This isn't actually a real picture. But the tiny black hole sitting at the center, feeding off of this star nearby. This process, how the black hole feeds off of nearby objects or gas, is what I'm going to be focusing on. There are, of course, other ways you can see black holes. They have very strong gravitational pulls. And so this other image is another artist rendition of what this might do to light. So the light, if you have a black hole between you and someone else, say between you and me, all the light that's directly behind might get somewhat absorbed, but it'll also get bent around the black hole. This comes from the theory of gravity, and this is called gravitational lensing, and it's a way you can find black holes even if they're not eating anything. Bigger black holes also exist, and these are the ones I focus on more, so I'll be talking about them a little bit more than in this talk, but these are called supermassive black holes, and they are one of the biggest mysteries in astrophysics. So supermassive black holes can have masses up to 10 billion times the mass of the sun, and they exist in the centers of galaxies. So in the center of our own galaxy, there's a supermassive black hole. It's about 1 million times the mass of the sun. In the center of basically every other galaxy in the universe, there's one of these black holes. And they have profound effects on the galaxies around them. They can spew out energy at quite alarming rates. Don't worry, we're far enough away from the one in the center of our galaxy. It's not going to hurt us. These supermassive black holes were first discovered through efforts actually at Caltech. So the first supermassive black holes were found as quasi-stellar objects or quasars. So these were found when people looked at the radio sky. So they took an image of the sky at radio wavelengths, and they found all these bright dots. And they were really, really bright. They looked just like stars, but stars weren't known to produce radio waves like that. So they took telescopes at Caltech. So for example, if you drive a few hours south, you'll hit the Palomar telescope, which Caltech runs. And they went and took an optical image of the positions of these radio sources and did what's called optical spectroscopy. They looked at the light as a function of wavelength. And they were able to show that these were actually very, very far away. They weren't inside of our galaxy. They weren't stars like the ones we see around us. They're much further away, much more luminous. They're very, very bright for us to be able to see them like stars, even though they're much more distant. And these are supermassive black holes, billions of times the sun's mass, that are sitting in the centers of distant galaxies and consuming so much matter that they're producing very, very luminous emission. Of course, I already mentioned there's also a supermassive black hole at the center of our galaxy. This is called Sagittarius A star, roughly 1 million times the mass of the sun, 26,000 light years away. The Event Horizon Telescope has been a big effort in the last few years to take a picture of this black hole. And this is sort of a simulation showing what it looks like. I'll show the actual image later. This is prettier. But so this black hole is sort of sitting and slowly consuming matter around it in the center of our galaxy, not nearly at the rate of quasars. The big thing to know about supermassive black holes is we don't know how they form. They're huge, they're everywhere, and we have no idea where they came from, and this has been a big problem in astronomy, and we've launched many telescopes to try to solve this, including the James Webb Space Telescope. One of the big science goals for that mission was to understand where do these supermassive black holes come from. And part of this is we don't understand fully how they grow. And so that's what I'm going to be focusing on for this talk. How do supermassive black holes feed and grow? And some of this will also apply to stellar mass black holes. So let's take a step back and look at the image of Sagittarius A star, the black hole in our galaxy. So what are we actually seeing here? The black hole itself is dark. We've already established that. And so that's going to be somewhere at the center of that image. I'm going to use a mouse a lot of the time to represent a black hole. The black hole itself is invisible. You can't really see it, except for the fact that it's consuming matter around it. This is the cookie. The cookie is very, very bright. This is why we're able to see black holes, because of this bright matter falling into it. But then why is the cookie bright? When you eat a cookie, it doesn't light on fire. Why does that happen with black holes? This is very simple. It's just friction. So first I want to define a quick term, accretion, which is the process of a black hole eating. It's just the fancy word we use for it in astronomy. But this accretion is luminous because of friction. As particles that the black hole is eating rub against each other, they generate heat. It's the same reason if you rub your hands together, they get warm, or if you try to light a match, it lights up. When you light a match, you're rubbing it against the box, it's generating friction. Then there's some chemical reactions that actually cause it to light on fire, but it's that initial heat you produce with the friction that starts the process. Near the black hole, this friction generates so much heat that this matter, these chunks of cookie it's starting to consume, can reach 1,000,000 degrees Fahrenheit. That's 20 times the temperature of lightning. So it's extremely, extremely hot. Because it's so hot, it's emitting these photons. These will be primarily in the X-ray wavelength, but I'll give you a bit more detail on what this actually looks like when we as astronomers try to observe it. And we can see them from very, very far away. And so this is why we usually find black holes, because they're eating. It produces this very luminous emission from this friction. But this leaves a few questions. Where is the food the black holes are eating coming from? How do black holes actually eat the food? I mentioned accretion, and I'll talk about disks a few times. Where does all that come in? What do astronomers actually see when we study these things? And how much can black holes eat? This comes back to this question of how do supermassive black holes form? Can you take something that's formed from the death of a star and is maybe a solar mass and grow it to 1 billion solar masses? Is that possible? Can black holes eat that much? So I'm going to go through all of this in a bit of detail. So we'll start with where the food comes from. What causes gas and matter to fall into a black hole? There's a bunch of different ways you can do it, and I've sort of picked 2 of the most common ones you'll see, in the case of supermassive black holes at least. So one thing that can drive gas towards a black hole is when galaxies merge. If you look in the universe and take a census of every black hole that's eating something, you'll notice a lot of them come sometime after 2 galaxies have merged. And a lot of galaxies are merging. Our galaxy is very, very slowly merging with another nearby galaxy. And so when galaxies merge, it causes this sort of lump of gas to form, right? It's not a sphere. If you have a perfect sphere, everything's just going to keep orbiting the black hole happily. Nothing will ever fall in towards the black hole. But the second you start disturbing that sphere, you make it very aspherical, gas starts falling in. And that'll drive all of this matter into the black hole and cause it to light up and start accreting. Another way you can feed a black hole is if something denser, maybe not just some diffuse gas flying around, but something denser comes close to it, and stars can do that. So if you have a very unlucky star that ends up on a path that takes it within the event horizon of a black hole, it'll get consumed and shredded. This can happen for stellar mass black holes, like this image which I showed you before, but it can also happen for supermassive black holes. So once every, say, 10 to the 4, 10 to the 5 years, for every black hole, every supermassive black hole in the universe, an unlucky star is going to get too close to it and get shredded, tidally disrupted, is what it's called. It's spaghettification, if you've ever heard that term. The star will get pulled apart and consumed. But the process of accretion is largely the same. How the black hole eats the material is largely the same in either of these 2 cases. And so let's talk about that in a bit more detail. How do black holes eat food? So if there's only a little bit, you're just throwing the occasional cookie at the black hole, it'll just chomp it up as soon as it gets it. It'll just slowly fall in. But once you increase the amount of material enough, it forms a accretion disk. So here, this is an artist rendition again. We don't actually have any pictures as pretty as this. We do have some cool ones though. You have the black hole in the center, and a ton of mass is trying to consume around it, and it forms a disk. This disk can be light years in size. There's a huge range. So why does it look like this? Why is it that most black holes, when they start eating, they form this disk of material once there's enough food? So why isn't it just that there's a blob of gas that the black hole is slowly consuming? So let's take the case that we have our black hole, which is our mouse, and it's surrounded by this blob of cookies. And the cookies are orbiting the mouse. Sorry, I'm going to really destroy this metaphor, but we're going to try to go with it. So we have our cookies orbiting our black hole. As they are orbiting, they're going to bump into each other and lose energy. Remember, there's friction. That creates energy loss, okay? So they're bumping into each other and losing energy, and they're going to try to fall into a geometry that has a lower energy state, where they're not bumping into each other as much and just continually losing energy. And what happens is that ends up being a disk. A disk is a state that has a very low energy. They're not going to bump into each other that much, but it has a key property, which is it conserves angular momentum. So angular momentum is something we love to talk about in physics, especially conservation of angular momentum. Basically, something that's spinning has to keep spinning. So you can't have all of these particles spinning around a black hole or all these cookies spinning around a black hole and then have them just fall in. This is the same reason if you've ever watched ice skating or really anything spinning, you'll notice if someone's ice skating and they have their arms out, they'll move at one speed, but if without moving at all, they just move their arms in, without moving any other part of them, they move their arms in, they'll start spinning faster. Okay, so this is conservation of angular momentum. You can sort of test this at home if you have a chair that spins and you move your arms out and in, or you go to a playground, okay? So this is the same reason that black holes form accretion disks rather than accretion blobs, okay? So what does this actually look like as an observer? So now we've established that we have a black hole with a ton of matter coming into it in a disk. And what's amazing about black hole emission is it happens at every part of the electromagnetic spectrum, which is why it's been really fun for me to do my PhD in this, because I get to use every single telescope you could possibly think of. It's awesome. So as I mentioned before, the material right near the black hole, that's where the friction produces the most heat. This material is really, really hot, 1,000,000 degrees Fahrenheit. This emits in the X-rays. If you go a little bit further out, it starts to cool down, so you can get visible emission or optical emission. Even further out, you can get infrared emission. I'll also just briefly have a divergence. You notice this little thing that's coming out of the black hole and going up. This is another phenomenon that accretion disks allow. It's called a relativistic jet. So basically, for reasons we don't really understand, black holes can occasionally spit material nearly at the speed of light and it's a galaxy. At extreme energies, it can propagate out beyond the edge of a galaxy. How they do this, something to do with magnetic fields and spinning. We don't actually understand it fully. It's a hot topic in astronomy right now. But what's key is it can produce emission in radios. So if you've ever heard of the Very Large Array in New Mexico, is featured in the movie Contact. That telescope has been used extensively to try to understand how these jets are launched, why black holes can spit this material out, and how it affects the galaxy around it. Because these jets, as I said, can propagate out beyond a galaxy. So here, this little central thing you see is a galaxy, and then these streams coming out perpendicular are the jets. They're so big that they can impact the outer regions of the galaxy. They can trigger star formation. They can turn off star formation. They can really do anything and inject tons of energy into their surroundings. So galaxies wouldn't look the way they do if we didn't understand how black holes and these accretion disks can launch relativistic, or if we didn't have black holes and accretion disks launching relativistic jets. But again, this is something we don't really understand. I'm not going to get into it anymore, but I highly encourage you to read about it if you're interested. It's a really cool subject. So let's take a step back to accretion disks and just say, putting it all together, what does a galaxy with an accreting supermassive black hole look like? The main point I want you to take away from this is how bright it can be, okay? So on this axis, it's basically different parts of the electromagnetic spectrum. So infrared wavelengths are here, so these are Largo wavelengths. Optical, so visible is here, and then moving into X-rays over here. And then this axis is brightness, okay? This gray line is what a galaxy might look like. So you take a typical galaxy, and you see what its emission looks like at all the different parts of the electromagnetic spectrum. You don't need to worry about the details. This black line is the sum of all the different things that accretion disk can produce, okay? So as I said, One part of the accretion is the inner part produces X-ray emission. Optical emission is a little bit further out, and then infrared emission is even further out. And it completely dominates the galaxy. And this is what's amazing, is that you can look into these distant galaxies and all you see is this tiny little black hole at the center blowing everything up. And you can see it across the electromagnetic spectrum. So as astronomers, we spend a lot of telescope time studying this light across the electromagnetic spectrum and trying to understand things about black holes. What do we actually learn, though? So I'll highlight a few different points. In particular, studying the accretion emission lets us understand where black holes live and how they affect galaxies. So I've already sort of mentioned this. These relativistic jets can impact their galaxies. In general, black holes, by accretion, are producing a lot of light that can propagate out into the galaxy and affect how it grows, how it evolves. So this is an image of a galaxy. And so you can see the galaxy in the top right corner in visible light. And then X-rays, so you can see this bright dot in the middle, that's the black hole. And then the radio, that's these jets I told you about. And then put it all together. But you can see how the black hole is affecting things on much larger scales than the black hole itself. We can also use the accretion emission to understand general relativity. So general relativity is this theory of gravity put together by Einstein. There still are questions about the model, and there's parts of physics we don't understand. Well, one thing about black holes, and this is what the Event Horizon Telescope was trying to do, was if you have some of the accretion emission around the black hole, there's going to be a shadow in the center. And that's because there's a black hole, and you can't see the light that's coming from directly behind. It's getting absorbed by the black hole. It's falling into the black hole's gravitational pull. And the size and shape of this shadow, this little black dot here, is governed by general relativity. And so when this image first came out, so this is the actual image of Sagittarius A star, the black hole at the center of our galaxy. When this came out, when the AHT first put it out, they showed that the size and shape of that little black circle is exactly as predicted by Einstein's theory. And now there's other efforts to keep pushing that and really probe whether Einstein's theory is completely valid. And the final thing that I'll mention about what we can learn about black holes, and what I'll focus on for a little bit after this, is how do black holes grow? So I've already mentioned, they can eat things, they form this accretion disk. But if you do a census of how much black holes are eating around the universe and how big they are, you'll find some weird things. And in particular, the James Webb Space Telescope has been key in finding black holes that are really, really big, but at the very beginning of the universe. Okay, so this image here shows a composition of X-rays. So the purple is X-ray emission, and everything else is from the James Webb Space Telescope, so it's sort of infrared emission. If you look in this little square here, there's a bright X-ray source with a faint little dot in the infrared. And so this was shown to be a black hole that is accreting, but the black hole is 10 million times the mass of the sun, but it exists in the early universe. So this happened when the universe was only 450 million years old. That seems very old to you, but if the universe right now was 50 years old, it'd be when it was 2 years old. So the universe is a toddler. Okay, so at the very beginning of the universe, when it was still a toddler, we've already got something that's 10 million times the mass of our sun. And so the question is, can black holes eat enough cookies to get that big that fast? Okay. So black holes must be able to grow really fast for this to be observed. But how do they do it? Is that possible? And so let's think about how fast a black hole can eat. So if you keep trying to feed a black hole, is there a limit to how rapidly it can consume matter? Can you have a black hole become 1 billion solar masses in an instant? And so the answer, as you could probably guess, is going to be no. So let's consider a black hole that's trying to eat as much as possible, or a mouse that's trying to eat as many cookies as possible. What's going to happen? The first thing that's going to happen is this friction I talked about. It's going to heat up the material, particularly in this inner region where everything is densest and the friction causes the most heat. So everything gets really, really hot. And what does heat do? It produces photons, or light, right? And one thing you may not know about light is it actually exerts a force. It can push things. So if you've ever gone and stood outside in the sun and felt heat on your hand, that's actually because of this. The light is putting energy into your hand. If it were a lot stronger, it would actually start to push your hand down. The light near a black hole is luminous, and so it starts pushing on the matter around it. This is the same reason why some satellites, if they get too close to the sun, they start to get pushed. And when NASA launches missions, they have to take that into account, that if things are getting close to the sun, this radiation pressure, the pressure exerted by the photons, will start to move things, okay? And so what happens is all the food is blasted away. If the black hole tries to eat too fast, if it tries to eat too much stuff at once, it gets too hot, and all the matter gets blown away. And this creates a fundamental limit in how fast a black hole can consume matter. You can't do it infinitely fast. This is called the Eddington limit, if you want technical terms. And it's just how fast a black hole can eat before radiation blows away the surrounding material. So just for a few numbers, this million solar mass black hole at the center of our galaxy, it can eat about 16 Earths every day if it wants to. It doesn't want to. In fact, I'll talk about that later. But it can eat that much every day before this happens. For a stellar mass black hole, it's a lot less. It's about an Earth every century. What you find if you actually calculate this is that the amount a black hole can eat scales perfectly with the mass of the black hole. So a more massive black hole can eat correspondingly more food at once, okay? And so if you look at the black holes in the universe and how much they're eating, we actually do see some that are eating at this limit. There's a huge range though. And so this plot here shows increasing black hole mass in this direction, and then increasing accretion rate, or how fast it's eating, is increasing going up. And each little point here is a different black hole that we've observed at some point. These lines, so this line corresponds to this Eddington limit. So this is theoretically the fastest a black hole can consume matter. This is roughly 10% of that limit. This is 1%. These aren't all the black holes we know of. That's why this part of the diagram is not very well populated. These are some that have been discovered with the James Webb Space Telescope. And you can see there's a whole bunch sort of hugging this line. Nothing goes that far above it. These lines are error bars, and they're all relatively consistent. If this means that this limit is true, which it seems like it is, it makes sense, then black holes shouldn't be able to grow infinitely fast. They can't break this Eddington limit. And so that black hole I told you about, the really, really big one when the universe was a toddler, couldn't have formed by accreting. It must have maybe merged with a bunch of other really big black holes, or started out that big to have formed. The issue is if you keep looking with the James Webb Space Telescope, you start to find things that are way, way above the Eddington limit. So actually you can break it somehow. And so this is an example of a black hole that was recently discovered. So this is an image of the galaxy where different colors are different wavelengths, so different parts of the electromagnetic spectrum. And then zooming in on the center, well, that's an artist's rendition, but you get the idea. There's a black hole accreting really, really fast at the center of this galaxy. So what happens if you put this galaxy on the plot we looked at earlier? It's way above this black line. It's accreting way too fast for basic physics. If this is real, then all I just told you about photons blowing away all the material can't be right. But it's basic physics. You know, we've been thinking about it for decades. We have no reason to think it's wrong, so there must be something else going on to be able to have a source that's accreting that fast. So how do you eat more than the Eddington limit? And this is really an open question in astronomy. For example, this image here shows a simulation of super Eddington accretion. That's what we call this, accretion above the Eddington limit. So all this white stuff is gas that's being funneled into a black hole. I'm only showing you half the system here. So in reality, imagine this is mirrored on the other side, and you have, it's not really a disk anymore, it's sort of this puffy structure. And these lines show the direction the gas is moving. And so you can see there's some gas sort of starting to fall in, but then some stuff, it's very low density, which is why you can't really see it on this plot, being shot out. And so and this is a simulation run by some astronomers at Harvard. And so what they've realized, and what other people are finding, is that you can break this limit for a few different reasons. One, you can do it if you have this puffy disk. It's not really a disk anymore, but if it gets really puffy, you can start to break things. Okay, sorry. You can start to break this limit. If you have lots of gas outflowing, this is sort of like those jets I showed you earlier, really fast gas moving out, you can start to break this limit. Or if you just only do it for a very short time, it takes light some time to push all the material away. So some combination of these things might allow us to break this Eddington limit and grow black holes really fast. And this is something we're trying to study really, really hard right now, because the more we look with James Webb, the more we find these black holes that are accreting way too fast or way too massive at the very beginning of the universe. And so the only way we could possibly have formed them is if they accreted a ton of material very quickly. But this is actually only a small fraction of black holes. We study them because they're bright and they're exciting, but many black holes, if not most black holes, are actually barely doing anything. They're just sort of sitting there, maybe not eating at all, or only eating a little bit. In Sagittarius A star, this image is the EHT, Event Horizon Telescope image of Sagittarius A star, is an example of this. It does have an accretion disk, but it's a very small one. The size of this is about a few solar systems. As I said before, it could eat 16 Earths a day if it wanted to. It's eating roughly 1 Earth every 1,000 years. Why is that? There's a few different reasons. Remember I told you earlier that one of the ways to feed gas into a black hole is to have merging galaxies or something like that? May just not have happened recently enough. So we have to wait till the Milky Way merges with another galaxy, and then maybe Sagittarius A star will be triggered to start accreting very rapidly. It seems like a good fraction of black holes are in this state, like Sagittarius A star. We know about Sagittarius A star because it's very nearby. It's only 26,000 light years away, which in the grand scheme of astronomy is actually very, very short distances. And that means that you don't have to have a very sensitive telescope to detect this emission. This emission is very faint, but we can detect it. I mean, it is still a very faint object even with normal telescopes, but we have some hope of detecting it. But if you took Sagittarius A star and put it in the distant universe, it's completely invisible. And so this becomes an issue. Many black holes are too faint to detect. If they're not eating that much, they're not producing that much heat, they're not producing that much emission. And so a big question in astronomy is, how can we find black holes that aren't accreting? As I mentioned before, one possible way to do this is with gravitational lensing, so the effect the black hole has on light coming from behind it. There's other methods, and I encourage you during the panel to ask one of our panelists, Pranav, who works on this sort of stuff. I know you probably didn't want me to call him out, but so this is an active area of astronomy. Another way you can do it is looking for black holes that aren't currently eating anything, but maybe temporarily do. So that's something I work on, is trying to find black holes that have briefly been fed an object. For example, if you throw one star at a black hole, the black hole won't be doing much most of the time, but then for maybe a few months, it'll suddenly become extremely bright. And so part of my thesis is trying to find these black holes that suddenly became very bright for a very short time, and using them to understand the rest of the black holes that didn't do that, but that we can't see. And of course, there's many other things we want to know about black holes and how they grow, other than how you can break super Eddington accretion and how you can find the black holes that aren't accreting that fast. So one question is, how fast do most black holes accrete? Not the most rapidly accreting ones, these super Eddington sources, not the least rapidly accreting ones, the ones that just aren't doing anything. But what's the distribution of this? And what can that tell us about the typical growth rate of black holes, how much they usually grow throughout cosmic time? James Webb has been crucial for studying this. So these images are, believe it or not, galaxies with black holes. They're called the little red dots. They were an unexpected discovery by James Webb. And they are supermassive black holes in the early universe that are accreting very, very rapidly, but for various reasons are hard to see. One of which is they're surrounded by what astronomers call dust, which basically prevents us from seeing the optical light. The dust scatters the optical light away, and we don't see it. And it absorbs the optical light. And so they're much fainter in the optical because of that, but because James Webb is able to pick them up, we can suddenly see them. And in general, James Webb is finding these fainter black holes that are otherwise undetectable and helping us fill in this distribution of how black holes accrete over time. And what we found so far is everything we thought before was probably wrong. There's actually a lot more black holes accreting at very different rates from what we expected based on previous studies. but there's a lot more work to be done. We still don't understand a lot about these sources. I've also described accretion disks as though, other than in the Super Eddington case, we know what we're talking about. But in reality, what I would say one of the biggest problems in astronomy is we actually have no theory of accretion that works. We know that every single model we have is broken. We use them anyway because we don't have anything better, but we're trying to understand exactly what accretion disks in this accretion process looks like. So how do we know that everything is broken? A big part of it is because there's black holes that produce these bright flares in accretion on month timescales. So you'll be watching a black hole that's sort of just accreting its normal material, and then suddenly it explodes and it produces a ton of accretion. And this isn't predicted by any of our models. There's no reason a black hole should do this, suddenly start accreting over days or months, suddenly boom in accretion rate. An example of this that's sort of fun, and if you Google it, you'll definitely be able to find some horrifying pictures, so I don't recommend it. We call it Scary Barbie. So the reason for that is this was an event detected by various telescopes, including the Zwicky Transient Facility, which is an optical telescope that monitors the sky every few days. And it detected this optical brightening of a galaxy. You can see that here. So this is an image of a field. There's some stars. But if you look at this little yellow circle, there's nothing there. And then this is an image with the Zwicky Transient Facility from some time later. You can see the same stars. It's different colors, but they're the same positions. You can sort of match them up. And this is where that little yellow circle is. Suddenly there's a bright source there. And that's a black hole that on a month timescale exploded. It was given a name that was a random string of letters that happened to have some of the same letters as Barbie in it. And this was also the same time that the Barbie movie came out. So they didn't really have a choice. And it was scary because it was so bright. So Scary Barbie. And so this is a black hole that suddenly began consuming huge amounts of material near this Eddington rate. And there's no model of accretion disk where suddenly half of the mass in the accretion disk is dumped into the black hole. That's not predicted by anything we can think of. And so we're trying to understand now, what do accretion disks actually look like? What model would do this? One possibility is accretion disks have very strong magnetic fields in them. We don't really understand where they come from or how strong they are, but maybe we're getting that wrong. Or maybe it's we don't understand exactly what's in an accretion disk. And so this has been a really exciting field of study where people have realized that accretion disks are big, and you can actually have stars that form in them and live in them. They can explode. You can get supernovae inside accretion disks. And there's a professor here at Caltech who's been studying this and finding some insane events. He found one he recently called Superman, which is another black hole doing something crazy. He originally called it, I think, Scary Ken to match up with Scary Barbie. Decided not to go with that. And so this is a picture of what this might look like, where you have an accretion disk, but if you zoom in a little bit, you'll see stars within the accretion disk. And when those fall into the black hole, that produce these giant flares of light, or when they explode, they might trigger mass to be shot into the black hole. And this is extremely new. We've only been thinking about this for the last year or so. So we'll see if we can actually prove it one day. And so we're continuing to work on this. As I mentioned, just recently, we launched the James Webb Space Telescope, where a big part of the goal was to search for the faintest and the most distant black holes to try to understand this accretion process and the range of accretion you can get and how much you need black holes to accrete, as I've shown you. Another telescope I'm really excited about that's going to be coming online in the next few years is the Rubin Observatory. So the Rubin Observatory is going to be monitoring the sky every few days and looking for things that change. And in particular, it'll be able to catch black holes that are suddenly starting to eat. So if you see something like Scary Barbie or Superman, these black holes that suddenly explode, it'll find thousands of them. If we've been able to find one now, it'll find thousands. In my thesis work, I study stars getting consumed by black holes. These are not black holes that already have an accretion disk, but they're just sitting there and then a star comes in. Again, we'll find thousands, tens of thousands of them. And so this is going to revolutionize this field of black hole accretion. So I'm hoping very soon to be able to start playing with the data from this. But all right, I'll stop there. Thank you so much for listening, and I'm happy to take any questions.
We can take a few questions. Yeah.
I might need you to like do a little scrolling because I think it was the fifth to last slide. Yeah. Oh wait. Yeah, that one. So I was wondering in the picture, what does Z mean?
So Z actually is a measure of where the black hole is in the universe. So it means redshift. So redshift is basically how we measure time in astronomy. It's because if you've ever heard of the Doppler effect, so like if an ambulance comes driving by and you hear that the sound sort of changes as it's moving towards you and away from you, we have a similar sort of phenomenon in astronomy, whereas things get farther away from us, the light gets redder as they get further away. So the light we observe seems to get redder. And we quantify this with this thing called redshift, which we call Z, which effectively translates to how far the source is away from us. So present day, we call redshift 0, so Z equals 0. Redshift 5 is very early in the universe. I'm going to say it's probably hundreds of millions of years after the Big Bang, whereas now we're 13 gigayears after the Big Bang.
Additional questions? Yeah.
And apologies for the lack of slide numbers.
Yeah, really cool talk. Thank you so much. Yeah, I had a question in terms of what a black hole eats or what gets secreted and actually goes inside. I'm wondering, is there, I mean, we wouldn't have any way to know, I'm guessing, but based on like models or theories, would what's inside the event horizon, like actually inside the black hole, would that change depending on what matter goes into it? Like if it's consuming a massive star that's made of certain elements or another black hole or something, like does the actual black hole change in any way based on what it's eating?
Yeah, so the actual interior of a black hole, I have no idea what's in there. If you could figure that out, you'll get a Nobel Prize. What can change is, well, obviously the black hole mass. The black hole grows as it eats things. It can also somewhat affect how the black hole is spinning. So black holes can be described by their mass and their spin are the primary parameters. And so, for example, when you have two black holes merge, if they both are spinning, the final black hole's spin will be different. It'll be sort of the sum of the two black holes spin, something like that. General relativity will tell you. I'm not an expert, but so as a black hole eats, it affects how it's spinning. Beyond that, what's inside a black hole, who knows?
You can watch Interstellar and get some hints as to what happens inside the accretion.
Those supermassive black holes that existed in the very early universe that, just they didn't have time to get that big. Could they perhaps have come from pockets of the Big Bang that maybe just didn't expand as quickly as the rest of the universe? Or could they have come from a completely different origin from what we normally know about black holes?
Yeah, I haven't heard of any models like that. That would be very interesting. Most of the models I know of, so one way is that they grow really fast, like I talked about. Another way is if you have, so early in the universe, you had a lot of gas everywhere. And sometimes you would have a cloud of gas that was so massive it should have collapsed into a bunch of stars, individual stars. But if you shine a really bright light on it, if you shine a really bright flashlight effectively, it'll keep it from collapsing and it can just stay there as 10,000 solar masses of gas just sitting there. But the second that light dims, it'll collapse. It'll stop being hot, right? Once it starts cooling, and it'll collapse directly to a black hole. And that way you can get a black hole that's something like 10,000 solar masses. It doesn't need to grow that fast. So you can stop breaking the Eddington-Limit. So that's sort of the most popular alternative model for how these formed. And in some ways, that's starting to be favored if we keep finding black holes that are so early in the universe. Although we are also finding ones that are actively super Eddington accreting. So we'll see. James Webb, I think, will help us solve a lot of these problems.
Thank you.
Hi. Could you please kind of further explain what you meant by when the accretion disk gets puffy? And
Yeah, so we often just talk about accretion disks as disks because of these very early models that showed if you assume the most basic physics, they're sort of just these disky shapes. But what we find is in practice, the second you start changing things a little bit, they start to not be these thin disks anymore. So by thin disk, I mean that the width of the disk is maybe like less than 10%, 1% of the size of the disk in the other direction. And so what happens in the super Eddington case, for example, is there's so much radiation that it starts heating up the inner part of the disk, and that gets bigger. And so you'll have a disk that's like got this puffy inner region, so it's like a little ball, and then maybe it's a normal disk after that, okay? And in that inner region, it gets so puffy that the way that energy is transported becomes different. It's this thing called advection. So it's basically the motion of particles that allows energy to be transported outwards. And that's what starts to break the Eddington limit, that you don't actually have as much radiation because you've changed the structure of the accretion disk. It's if you assume this very thin disk that you have problems. And that's why people originally thought this Eddington limit had to be followed.
All right, let's thank our speaker. And now we're going to have a brief intermission. So I encourage you, we have telescopes set up outside. We're going to set up our Q&A panel in here in about 5 minutes. And both events will go until about 9:45. And you're free to go back and forth between the two, asking questions here of our panel or looking through the telescopes outside. Our next event will be Friday, May 2nd. And our next Astronomy on Tap will be a week from this Monday, April 14th. Okay, we'll start our panel in just a couple minutes. Okay, thank you guys for sticking around for our Q&A panel. What we'll do is we'll each go through and kind of introduce ourselves and the science that we work on, so you have an idea of what our expertise is. But you should feel free to not be limited by in your questions as to just the expertise of the panel. Ask whatever questions you want. I mean, related to physics, astronomy, space, these sorts of things. We don't know all of the answers in the world, but we know some of the answers associated with astronomy, and then we'll try and address whatever question. So I'm Cameron Hummels. I'm a research scientist here and the director of astrophysics outreach. My science is primarily in galaxies and studying how galaxies form, how they change over their lifetimes. Sometimes a little bit dealing with the black holes in the center, but less. That's a focus of my research. And I mostly do this through computer simulations, big supercomputer simulations that try and model the behavior of these things and how they evolve over long time scales.
Well, folks sort of heard what I do. But yeah, so I'm Jean. I'm interested in black holes, primarily in the supermassive regime or close to it, and trying to use different methods and different types of data to find them and learn about their growth.
So I'm Elias. I'm a postdoc here. I also work on supermassive black holes only. I try to understand how they grow. I study a lot the accretion disk that Jean mentioned. I study how the light is distributed there. How are the different wavelengths that Jean mentioned. So I study them. I study how we can map the regions around the black hole, how they grow, how they evolve. So I study the ones that are very close to us and the ones that are also very far from us at different wavelengths. And I also do some simulations, some modeling, trying to get a full picture of what we are seeing.
Hi, I'm Pranav. I'm a third-year grad student here at Caltech, and I work on discovering and characterizing binary star systems in our Milky Way galaxy that host a stellar mass black hole or neutron star that's orbited by a normal luminous star. And specifically, I'm interested in finding those black holes and neutron stars that are not eating or accreting matter from their luminous companion, or their so-called dormant neutron stars and black holes. And it's important to find and study the systems because while they are much harder to find than accreting systems, they don't give off the same amount of electromagnetic radiation, they're actually theoretically expected to be far more common than the accreting systems. So it turns out that only a few special black holes get those cookies. And so the way I try and find these systems and think about finding them is through the motion of their luminous companion stars on the sky as they wobble back and forth, tugged by the gravity of their hidden and unseen companions.
Okay, great. One last announcement I wanted to make before we get started with the Q&A panel. Virtually all the science that we're talking about tonight and that you've heard about that are done at these past events is done through federal funding of science through NASA, the National Science Foundation, and so on and so forth. And I just wanted to make it clear, much of the funding for the work that we do and people at other institutions working on space and astronomy is largely through taxpayer-funded resources. And we thank you for that. And part of the goal of this is to, pay back and teach you guys something of what we've learned using the funding you've graciously provided. Anyway, okay, I open it up for questions. Does anyone have a question for the panel?
So it was mentioned that if two black holes collide, the spin of the resulting black hole would be the sum of the two. Is it possible for the two black holes to be spinning at the same speed in opposite directions? Like, what would happen if that happened?
Yeah, so you can have black holes that, well, I believe you can have black holes that start with spin and end up with no spin by mergers. I will admit this is not exactly what I work on, so I'm not an expert, so if anyone else wants to jump in. But yeah, so when black holes merge, you can change the spins in any way possible. And another fun thing it can do is when two black holes merge with spin, it also affects happens after the merger in terms of how fast the black hole is moving. So if you have two black holes that merge and they're spinning, they can get kicked afterwards and go flying out. And so this is actually a really fun thing that I've been starting to think about, because if you have two black holes, say even supermassive black holes, maybe not quite that massive because those are pretty big, but say 10,000 times the mass of the sun that merge together, it can get kicked and go flying out of its galaxy. So you can have black holes just wandering around the universe because they've gotten this kick from the merger, which is in part a function of what their spins are. And so part of what I'm trying to do is find these wandering black holes that are just meandering through the universe.
Yeah, so actually also astronomers here in Caltech a few months ago discovered that one of those happened. And actually what happens is that, so Gene was mentioning that the supermassive black hole, usually we expect it to be at the center of the galaxy. And then astronomers here using Palomar, what they found is that there's a galaxy, but there's a very bright blob that is not in the center, but somewhere at the outer parts of the galaxy. And we think that what happens is that there was a merger, and this black hole, a very massive black hole, was kicked, and it was now moving away from the central part of the galaxy. And also depends on how the black holes are spinning and in which direction. So the spin may cancel out, or it may add. So there are different ways of dealing with the spin. So at the end, you may have a spinning black hole when they merge, but it depends on the initial directions of how the black holes are rotating that you may have aligned or misaligned or canceled out.
Thank you. Great talk. If you can't see a black hole, what's actually spinning? You're talking about spinning. Is it the media right around it, the superheated material that's got the high friction? What's actually spinning?
Everything's spinning. So
what are you seeing?
So practically, you can imagine the black hole as a ball that is spinning on its own, that is moving, rotating around itself. But also the accretion disk is practically rotating. So it can happen that the direction in which the black hole is rotating around its own axis, around itself, and the way that the gas in the accretion disk is rotating, they are going in the same direction. Or they can be that one is moving in one direction, the other is moving in another direction, and you have a completely different signatures in terms of light when you have what we call retrograde or prograde motions.
And I'll just add, in terms of the actual black hole spin, one of the ways that we observe that is the way the black hole is spinning affects how close matter can get to it. So this event horizon can shrink or grow. It's a function of the spin. And so general relativity predicts exactly how that happens. And so if we can study that, that tells us something about the spin. And the spin itself is sort of related to this conservation of angular momentum idea I mentioned during the talk, which is, you're feeding stuff into the black hole that's spinning. Black hole is going to sort of keep spinning. That's one way you can think about it.
One thing to add is it's weird to think, and you pointed this out, it's weird to think about these things as rotating. It's kind of like electrons. Electrons, we know electrons have spins associated with them, but basically from our perspective, it's just like an infinitesimal point. So how can something like that be rotating, and how can we measure it? It's not entirely clear, especially because the theoretical model behind a black hole is that all of the mass is concentrated in this infinitesimal, infinitely dense point in the center. So if it doesn't have any moment of inertia, what does it mean for it to actually be rotating? But it appears to be some fundamental spin parameter that's associated with these things that doesn't fully fit with the model that we have this everything contained in a single point. So you bring up a really relevant point that's one of the challenges in the models that we have for these exotic structures.
Thank you very much. Great talk. So it looks like you are able to measure the mass of black holes all the time. And sometimes I imagine can be easy, sometimes could be difficult. Could you perhaps explain easily how you measure the mass of a black hole and when it's easy and when it's difficult?
I'd say 99% of the time it's extremely difficult. This is actually one of the most fundamental problems, I'd say, in black hole physics is how do we get their masses? So I'll comment more on the supermassive black hole side, and then maybe Pranav can talk about for stellar mass black holes. For supermassive black holes, for the black hole in our galaxy, Sagittarius A star, we can watch stars orbiting around it. We know how objects orbit a massive object, and from that you can infer the mass of that black hole. Once you get to most any other black hole, you can't see those stars anymore. They're too far away. And so we sort of use various calibrations to do it. So there are some black holes where we can see different objects moving around them. You can see stars or gas moving around the black hole, and there you can infer the black hole mass. This is called a dynamical mass measurement. If you get even further, just slightly beyond what we call the local universe, so nearby galaxies, you can't do that anymore. It's impossible. And so there, what we learned is if you make a plot of black hole mass versus galaxy mass, there's a fairly tight correlation between the two. You could also make a plot of how fast the stars in the galaxy are moving, how fast they're rotating, because in a lot of galaxies, stars rotate, versus black hole mass, and there's another fairly tight correlation there. So for a distant galaxy, you can measure that galaxy's mass or its velocity, the velocity of the stars, you can infer a black hole mass. This, of course, assumes that these correlations are true for every type of galaxy, and it also assumes that it's true as you go to more distant galaxies, which are in the earlier universe, and it's not clear that that actually holds. And so this is actually, so a lot of what I study is these stars being accreted by supermassive black holes. And one of the original motivations for searching for this type of object was the hope was that this process of the star being consumed by the black hole was simple enough that we could model it and use it to measure black hole masses. We're getting close. We think we've almost-ish done it, but that's one of the big hopes, is that we have another way of calibrating black hole masses that might be a little more accurate. So it's a big problem. Yeah.
So Gene talked about the big black holes. I'll talk about the small black holes, specifically the stellar mass black holes that are in binaries, because that's what I study. And this is where that binary, that luminous companion star to the black hole really helps us figure out what the mass of the black hole is. Now remember, that black hole is tugging on its companion with gravity, and so that companion is orbiting the black hole. And in order to figure out how it's orbiting the black hole, we can do spectroscopy on that luminous star. We can take a spectrum of it, which is the light that we get from it as a function of wavelength. And we can see, okay, so there are specific features in the spectrum. We have a template for what we think that should look like when the star is at rest. But as the star moves back and forth along the line of sight from us to the star, we see those features in the spectrum move relative to the template. That's called the Doppler effect. And for the Doppler effect, you can also think about like an ambulance siren as it goes by you and how the frequency of that sound changes. You also see that effect with the light. And so by comparing a template against what you observe, you can figure out how that star is moving relative to you and along your line of sight. And then you can get what's called a spectroscopic orbit of that star around the black hole. And that tells you two things. It tells you what the orbital period of that star is around the black hole as it moves back and forth. And it tells you also, roughly speaking, how fast that star is moving. And so those two pieces of information taken together can give you what's called a mass function of the black hole. That does not get you out of the woods, actually, because that's an entangled quantity that it depends on the mass of the black hole, the mass of the star, and another very annoying parameter, which is the inclination of the orbit relative to you in the sky. Remember, we see the sky in 2D, not 3D, but you can get these other two pieces of information. By studying that star itself, you can get an estimate of what its mass is, and then you have to look at other pieces of information to get an inclination constraint. There are two ways of doing this. One way is by tracking the motion of the luminous star on the plane of the sky itself. This is called astrometry. That can give you an inclination constraint, it turns out. Or you can look at how the light coming from the companion to the black hole varies as a function of time. There are methods that can also give you an inclination constraint there. And once you have all of these pieces of information together, you can finally disentangle what the mass of the black hole actually is.
It's hard. I promised some of the online audience that I'd ask their questions here before we move on to more questions from the in-person audience. One of them is, could there be a region around a black hole that could support habitable temperatures and a habitable environment? Like, could you, in the movie, and again, spoilers, in the movie Interstellar, there is a planet that's orbiting around this supermassive black hole, and you get some interesting time dilation effects. Do you think there's a possibility that you could have a planet that might be close enough to have, habitable conditions on it proximate to a black hole? Or would it just be irradiated too much?
Yeah, I can try this question.
Sure.
I have thought about this a little bit. Like if you have a star orbiting a black hole and then you have a planet orbiting that star, the question is really, could that planet survive the processes of binary evolution that led to that black hole being created in the first place? And there's some processes in binary evolution that would probably make it pretty difficult for such a planet to survive. The first is that the massive star that was the progenitor of this black hole is going to explode at some point. That's what leaves behind the black hole. So when you have a supernova, what happens to the planet? Also, when you have a very massive star that's orbited by, say, a less massive star, when the very massive, it depends on your orbital separation. Now, I imagine if that star and planet were very far away from the black hole, they could essentially survive all the way through. But usually if they're closer in, now the stars that are massive and they leave behind these black holes, they eventually reach a stage which is called a red supergiant. So our sun will eventually become what's called a red giant. And red supergiants their radii are like 1,000 times the size of our sun. And so you can see these stars becoming very, very big. And eventually they will start to interact with their companions. The size of these stars will become comparable to the orbital separation. And then you will see the star start to enter the atmosphere of the more massive star and start spiraling inward. And even then we start wondering, can the low mass star survive that process without merging? Think about what would happen to a planet, which is much smaller. So I would be pretty skeptical about a planet surviving all of this scenario, but I wouldn't rule it out completely.
So that all sounds reasonable. But what if you had a rogue planet just flying through space and it got gravitationally captured by an existing black hole that was already chilling out there? So it could potentially avoid this whole binary stellar evolution and just get on at the end when it's already a fully formed black hole. I imagine that could happen, and there's enough systems in the galaxy or in the universe that maybe this could happen. But I just wonder, if you get into that situation, would you be totally irradiated by radiation from the accretion disk that might make it a really unpleasant place to hang out on that planet? And I guess I don't know.
I would think about the dynamics of that situation, and is it more likely that the planet just falls into the black hole or scatters and flies off elsewhere versus just exactly getting into an orbit that allows it to survive? And you talked about the irradiation from a potential accretion disk and things like that. I would say, yes, you can make it happen if you really want to, but the chances are
low. Yeah.
Yes.
Okay. So possible, but improbable.
Basically, I'm saving the sci-fi. They're allowed to exist. Okay.
Okay. Questions from the in-person audience. Let me. Here. You have a question.
So speaking about the bright flares in the accretion disk that we're trying to solve that mystery, what are the other ideas we have about why this may be happening other than maybe stars forming and then supernovaing in the accretion disk?
So right now, I would say the stars forming is the most popular idea. I think there are a handful of other things. So as I mentioned, we don't understand how accretion disks work. And actually, until maybe 3 years ago, a lot of people preferred models where they're so-called disk instabilities. And so this is what happens when the disk enters a state that is unstable for some reason. Like it'll suddenly dump a lot of matter on the black hole. And so there were some predictions in, I think, the 70s and 80s for different reasons this could happen. And one is where you have gravity, you have radiation pressure that I talked about, and then you also have these magnetic fields. And if they get into a imbalance, which it was predicted that actually could happen in some of our basic accretion disk models, they could get into this imbalance that would cause like half the accretion disk to suddenly be dumped on the black hole. Or okay, maybe not half, a larger fraction than you would like. And that would cause a sort of flare where you would see a black hole that sort of just like burbling along, it's just accreting a little bit, and then suddenly all this mass gets dumped on, it shoots up for a bit, then it shoots back down. And so there were efforts to try to actually do simulations of this, including general relativity, including magnetic fields, including all of this physics. And every simulation, I think, had a different answer about whether or not this actually happened. It's a really hard problem to simulate this. The problem with accretion disks is, especially for these supermassive black holes, you have to think about physics on the tiniest scales and the biggest scales. These things are very, very large, but they care about physics of individual atoms. And so it's very, very hard to actually model these. But so this was a model that people proposed, some of these instabilities where you'd have magnetic fields go nuts or something like that. I think the reason they fell out of favor is because it was just really hard to get it to produce the right timescales for these flares. It tended to produce flares that lasted for decades, but Scary Barbie and some of the other events we're seeing are month timescales. They're just way too fast for any of those models, which is why people moved to stars falling into black holes. That change happened over a few years, so we'll see if it changes again in the next few years as more simulations come online and we discover more events.
So many questions. Okay, we'll get to everybody, I promise.
Hello. So my question is, can supermassive black holes exist in dwarf galaxies? And if not, why not?
So this is my absolute favorite topic. I love these. I want to find these so badly. So these are actually called intermediate mass black holes. As I mentioned earlier with the question about how you measure black hole masses, you could sort of predict for a given galaxy mass what the black hole mass should be. Supermassive black holes, we arbitrarily define to go down to maybe 100,000 solar masses. But then there's this region below that, maybe like 1,000 to 100,000 solar masses that we call intermediate mass black holes. And the reason we've divided it up, and these are the ones that we would expect to exist in dwarf galaxies and any lower mass galaxies. And the reason we've divided it up is because we can't find them. And so we've given them a different name. We're getting better. We're getting closer to finding them. The problem is they'll sit in the galaxy, but these little galaxies, so a supermassive black hole in a galaxy like the Milky Way goes to the center of the galaxy because gravity sort of pushes it there, right? If you're in the center of the galaxy, gravity's not pulling you in any direction. You can just sit there, it's stable, you won't move. In a dwarf galaxy, there is no center. They're all over the place. And so these black holes will wander around. They don't necessarily need to be in their galaxy. They can just be going off wherever. And so we don't know where they should be. And also because they're lower mass, they're fainter. So they're harder to find. So you have this problem of both you don't know where to look and you don't know they're going to be too faint to see anyway. It's a big issue. That's why I want to use these stars getting randomly thrown into the black hole to try to find them, because that'll produce a very bright flare that we actually have some hope of detecting. I thought I found one. I'm not as convinced anymore I did, but we'll see what other people think when they read my paper. But yeah, and so we're trying to look for these sort of transient accretion events to track them down, but they should be there. And if we can find them, we can use them to understand how the even more massive black holes form, because these really, really massive billion solar mass black holes formed from these little ones. And so if we can understand what they look like in dwarf galaxies, maybe we can understand how they formed into supermassive black holes.
I'll just add one note to that. So there's recently, like in the last month or two, there was a paper that was written partially by Karim El-Badri, who's a professor here, but the first author and the third author are at Harvard. And there was indirect evidence for one of these black holes in our nearest dwarf galaxy neighbor to the Milky Way. So the galaxy is called the Large Magellanic Cloud. You can't see it from in the northern hemisphere because it's on the it's in the direction that you can see from the southern hemisphere. And if you go to a really dark sky site, it kind of appears like the Milky Way does, kind of the same surface brightness as the Milky Way. So you wouldn't be able to see it from a city like Pasadena, but it's near the kind of southern celestial pole, and it's pretty, it's cool to see. But the piece of evidence, rather than, as Gene was talking about, we don't have any direct evidence like you can see the accretion disk or anything like that. But what they detected were these stars that were moving really, really quickly in our galaxy. They're called hypervelocity stars. And generally, stars shouldn't be moving so fast relative to to the rest of the stars in the galaxy unless they're propelled that way somehow. And so the current model for the generation of these super fast stars is that they get too close. They're in like a binary star system, and they get too close to a supermassive black hole, and they undergo a three-body gravitational interaction, like the book, like the show, but where essentially you get these two stars, they come too close to the supermassive black hole, one of them gets captured directly by the black hole, and the other one gets flung away at really, really high speeds. So you'd expect, and this is consistent with what they saw these hypervelocity stars like going in all directions. There was no preferential direction for most of the population, which is consistent with our own supermassive black hole of the Milky Way launching these in kind of every direction. But there happened to be a concentration of a handful of them that were all moving in the same direction, which is weird, right? Because you should expect it to be going all over. And if you trace back the trajectory from where all those stars were coming, they're coming from this Large Magellanic Cloud. They're coming from that galaxy. And the idea is that galaxy is moving in its orbit around the Milky Way, and it's also shooting them out in all directions, but they're going to be preferentially propelled along the trajectory of that galaxy. And so that's essentially what launched these things. So again, it's an indirect measurement, but it is suggestive that there is one of these kind of intermediate mass black holes in the center of the Large Magellanic Cloud that's launching. So go ahead. Yeah.
Yeah, I feel obligated to comment on this because my advisor is Kareem. And I after he published this or helped publish this paper on hypervelocity stars, I went to him and asked him, so does that mean we have evidence now of an intermediate mass black hole in the LMC? And he was actually, I think it's a supermassive black hole. So now we can argue over terminology. And what exactly is an intermediate mass black hole?
But good question. Good. And I like your shirt, your accretion disk shirt. That's pretty awesome. Here, we'll get a question back here.
I had a question about relativistic jets. So I've always been told that nothing escapes a black hole. And then earlier in your talk, Gene was talking about like relativistic jets and like, what is that? What kind of material is spewed out? And can you use that to find black holes? Is that possible?
Yeah, 100%. So
One sec before we get. If people haven't looked through the telescopes yet and they want to, they'll be closing them down in about 12, 15 minutes. So I encourage you to I know you probably want to hear the answer to this question, but if you want to look through the telescopes, do so in the next couple minutes before they start to shut them down. Go ahead, Gene, I'm sorry.
Yeah, so that's a great question. I think relativistic jets are one of the best ways we have to try to study black holes. I should qualify the material the black hole is shooting out. It's not really the black hole it's not ejecting stuff from within the black hole. It's more material from the inner edge of the accretion disk that's sort of sitting around the black hole that gets suddenly flung out. Exactly what's causing that, we don't know, but basically somehow in this process of accretion, there's a ton of energy being pumped in to some small fraction of the gas that's being accreted and causing it to get thrown out at nearly the speed of light. And these have always been so these quasars were first discovered because of these relativistic jets. I mentioned that they were first found as these really bright radio sources in the sky. And what that is relativistic jets pointed at the Earth. And when you have something moving the speed of light that's pointed at the Earth, there's this effect called beaming, where basically they appear a lot brighter than they are because they're moving so fast. And so you get these booming radio sources pointed at the Earth that look like stars, hence quasi-stellar objects. And so they were the way we first found supermassive black holes. And even today, we're finding more and more supermassive black holes because they're just so bright. These jets are so energetic, they're so bright, there's an easy way to find black holes. And you can look at their effects on the galaxy well after the black hole has stopped spewing out this jet and still see the impact. And so you can infer what the black hole was doing based on what the jet has done to the surrounding galaxy. You can see it like drills holes through galaxies as it propagates outward, and it leaves clouds of material on the outside of wherever it stopped moving that can have like clumps of star formation and things. And so this was actually when I was an undergrad at Princeton, I did a project on this, on a black hole that had launched out these extremely powerful jets to well beyond the size of the galaxy. And even though it wasn't still producing these jets, the jets had turned off. You could still see the after effects of them and use them to understand what the black hole was doing when it first launched them.
Related to that, we have a question from the online audience. Are jets from black holes essentially their burps? And do these jets feed the galaxy's material that can help start their formation or progress in their formation?
I think burps is actually a pretty good way to describe it.
Yeah.
I have seen that used, I think, in actual like papers. So yeah, for sure. And you can get jets where it's like sort of they launch a clump of material and then they'll launch another little blob of material. And so they turn into these little blobby things that are moving out at the speed of light. And sorry, what was the second part?
Oh, just if the material that gets launched could potentially be help as particularly from supermassive black holes in the centers of galaxies, are they feeding more material into the galaxy that could then, help it form or help it?
Yeah, I don't think it's
seems like it's launching
enough.
it so.
Yeah,
it's not that much, and it's launching it so forcefully that
exactly
it would disrupt more than like provide a seed.
Yeah, what it can do is cause, like, as it hits into clumps of gas, it can make them denser, and that can trigger the formation of stars. And so that's how black holes can cause star formation in the outskirts of a galaxy. For example, these jets hit gas and make it dense. The material from within the jet itself, I don't think would be enough to actually contribute much to that.
It's pretty low mass.
Yeah, it's pretty low mass. You can't if you tried to send out solar masses of material at the speed of light, it would take a ton of energy, and even black holes, I don't think, want to do that.
Just to add one more thing. So these are low mass and very high speed, so they escape the galaxy. So we see them escaping the galaxy, but this is a form of what we call feedback. So we have two forms of feedback, the positive and the negative. So the positive is when the ejected material, because so the black holes are accreting, but also some of them are also ejecting material. So they're also pushing energy and material through what we call wind. So similar to a wind that is ejected from the disk and goes and to feed the galaxy. So it has two effects. It can either quench the star in the galaxy and stop everything that's going there. And also it has a what we call negative feedback. And it also had the problem is that if you stop everything and you push everything out, so there's no more material that could go into the black hole. So as if the black hole is pushing out the cookies. It's not the cookies, it may be the dough before before making the cookies. Or it can help by making things, as Gene was mentioning, by making things more dense, so it can favor in some region forming more stars. So it goes both ways.
Okay, I get the guy in the back.
So I hear the term I hear the term like spin and like scattering. Does that imply that the mathematics that describe these black holes are like wave functions that describe electrons?
So usually the scattering, I think, that they're talking about isn't so much, I mean, certainly there are wave functions for describing things, but mostly macroscopic objects don't necessarily, the wave functions, the wavelengths are so small that it doesn't have a direct impact. I think when we were talking about scattering, it was more the scattering of the material off of if you've got a bunch of a cloud of stuff and you punch through it, some of that material scatters off the particles that are there, as opposed to a quantum scattering effect, that sort of thing. So,
yeah, definitely.
What would happen if a galaxy collided with a black hole?
So yeah, so if the galaxy, you have to think about the galaxy, it's much bigger than the black hole. So what happens usually is that we think that two galaxies could collide together, and when these two galaxies collide, so their black holes will collide also. So what happens is that the central mass of the two central supermassive black holes, they will go and collide. So they will orbit around each other, and then this orbit will shrink and shrink and shrink, and then they will at the end merge together and form another black hole. And when they are doing that merging, so they will generate kind of waves in the space that will travel, what we call gravitational waves, because these waves are caused by the gravity of these black holes, and then we can detect them. And there's a group of people here, that the LIGO collaboration, that are trying to find these waves that propagate from very distant galaxies and come to us. And then we think that these are due to the collision of two black holes.
Yeah, and I'll add, so this happens all the time, sort of black holes hitting galaxies, and it's for the same reason that really galaxies merge with each other all the time. Galaxies hit each other, and every galaxy has a black hole in it. And so effectively what you have is whenever two galaxies merge, you have a black hole that's falling into another galaxy. And people have tried to sort of simulate what effect this has. And so they'll simulate, a galaxy like the Milky Way. The Milky Way's had a ton of mergers. There's been little tiny galaxies that have fallen in, bigger galaxies. And what you get is tons of black holes falling into the Milky Way and orbiting around. And there are some models that actually predict there should be a ton of these black holes just sort of floating around the Milky Way, falling in slowly. Eventually they'll merge with the central supermassive black hole. And in some galaxies that are more massive than the Milky Way, you can get up to hundreds of black holes, not the supermassive ones, but slightly smaller ones, maybe 100,000 solar masses, that are slowly falling in to the center of the galaxy. Whether we'll ever be able to see them depends on if they ever interact with anything. So if they hit some gas cloud or they hit a star, then you'll suddenly see this burst of accretion. You could also maybe see some of the dynamical effects of this lensing I talked about, where light is bent by the black hole. But there may be tons of them out there if these simulations are right.
So related to that question, there's a number of questions online that are essentially talking about, can either the introduction, you talked about flinging a black hole kind of out of the center of a galaxy, or the jets launching material through the galaxy. Can these have a structural impact on the galaxy itself? Can they like disrupt a galaxy? Are they that powerful enough? Because we're talking about, kind of these bullets or these beams of material or a black hole traveling through it. Could it disrupt a whole galaxy or change the structure of it? What do you guys think?
Depending on how extreme your definition of disrupt is, I would say yes. These, black holes flying around, well, the black hole itself flying around might not actually do that much, because you do need to get pretty close to a black hole to actually see some effect. So black hole flying out, if you get lucky, you'll see something, but given that we don't know of many examples of this, it tells us it's pretty hard for this to happen. It's rare. But the jets flying out, they inject a ton of energy into the galaxy, and they completely change galaxy structure. As I mentioned, there's this correlation between black hole mass and galaxy mass. In principle, you wouldn't expect this to exist, because the black hole only affects the innermost regions of the galaxies. There's no reason it should know about the total mass of the galaxy. It shouldn't know how many stars are there. The reason it does is because the black hole injecting energy into the galaxy has changed how it's formed stars, so it's changed the entire evolution of the galaxy. And that's why there's a correlation between black hole mass and stellar mass. It's because the black hole has influenced galaxy evolution.
Oh boy, okay.
Regarding the Eddington limit, is it observed? We've observed, it sounds like things that break it, but we observed it actually in action. And if so, about how long does it take for the radiation to blow out the accretion disk, I think?
How long does it take? That's a good question. I actually don't know off the top of my head. So I think we more observe it on a population level, in that if you look at a bunch of black holes, you won't see many that go above this Eddington limit. Most black holes are going to be accreting well below it. I think in terms of timescales, it's probably longer than years at least, given that we see events that can definitely produce the super Eddington radiation for years, or never,
But that's for like supermassive, right?
Yeah,
I
that's
think
for
it's going to be
supermassive.
related to the size scale and the mass scale. So for very small things where the light crossing time is the size of, a a planet or something like that, I think it could happen more rapidly
Yeah,
in a
for
much
sure.
more massive, larger structure.
And this is something we like to try to take advantage of, the fact that little black holes have much faster timescales for all this to happen than the really big black holes, because it means if they all have the same physics, which they probably don't actually, but let's pretend that little black holes and big black holes behave in the exact same way. If we study what little black holes do, we can do it on the timescale it takes to get a PhD. And so then you can see all of this phenomena, measure all the timescales, and publish this great thesis where you've solved all the black hole problems, and then just apply it to the big black holes. In practice, that doesn't work because actually a lot of the physics changes as you get to the bigger black holes, but that's what a lot of people have been trying to do.
Makes sense. Do you want to add?
On that note, when you do have an accreting black hole binary where there's a luminous star accreting onto a black hole, it can get bright in the X-rays because of the accretion. You call this an X-ray binaries. X-ray binaries have accretion disks. X-ray binaries can have jets. In fact, there are certain X-ray binaries that are just called microquasars in analog to the large quasars with supermassive black holes. Now, again, not all of the physics is analogous, but you can see a lot of this physics on small scales.
Try and get everybody once first before we go to.
Yeah, accretion disk again. First of all, thanks for explaining why it's a disk and not a sphere. Now, initially it starts up as a sphere, and then it has to go into the low energy state. So what happens to those particles? What is the mechanics of those particles which are doing the wrong thing? And related to that is also the Eddington limit. It does not apply to cases where the accretion disk is not pristine, right? So initially, all black holes should feed at a super Eddington limit. Is that true also? So there are two questions related.
So first, for the super Eddington part, I think it's always really hard to break the super Eddington limit just because as long as you have a lot of material getting close to the black hole, it's going to get really dense and it's going to all rub against each other and you're still going to get this friction that heats things up, which is why you need this specific structure that simulations are starting to find, this puffy accretion disk I mentioned. We have sort of a puffy region and then the thin region. That's so far, I think, the only stable state this has been able to happen in. Any other geometry, you end up getting this all the matter getting blown away effect. And so that's why super Eddington states sort of exist or have to be in that form. Sorry, could you repeat the first part of the question? Sorry, Cameron. Oh, yeah, yeah.
Wrongly
yes.
Particles which are going
Sorry,
wrong.
so actually, if you look at the larger scale structure of an accretion disk, what you end up finding, and there's been work by people in the department, like a professor Phil Hopkins here, who've tried to simulate, full accretion disks. And you see there's this like disky structure on the inside. But as you go further away, it gets larger and larger, eventually merging in with whatever gas streams are feeding into the black hole. So you have these like gas streams coming in from every direction that'll sort of feed into this like structure that's disky at the center, but then gets very puffy outside and sort of turns into this spherical-ish or whatever the gas is doing, that structure as you go to larger scales.
Maybe more like a donut at large scales as opposed to a disk at small scales. Okay.
Hello. So say if you have two black holes, one rotating, the other one's non-rotating, charged or uncharged. Would you describe the space-time around it with the curve metric, or would you do Schwarzschild metric, or would you not do that at all?
So yeah, we don't know what's the real metric. In principle, the Kerr metric should still work. For sure, it's not a Schwarzschild. Well, Schwarzschild is a particular state of the Kerr metric, because so the metric is how you describe space and time around a black hole. So the Schwarzschild metric is assuming that the black hole is not rotating. The Kerr metric is a generalization of that by saying that the black holes are rotating. So you can go from the Kerr to the Schwarzschild by saying that the spin is zero, that the black hole is not rotating. In principle, it should hold, but we don't know if the Kerr metric is the reality or not. So all of what we are discussing here are models. So it's how we perceive or how we think the black holes and the universe is working. So it does not mean that it's 100% sure, but is the closest to reality and the closest thing to explain what we observe. Of course, every model has a limitation, but so far, so that's why we try to test them all the time to see where they break, where they don't break. And if they're breaking, if they're not working, we want to understand why. And that's how we make the improvement in our modeling, in our understanding of physics in general.
You have a question? Sorry, I'll get to you again, but. Pardon me, Cass.
I loved your talk. Thank you. Everything today we've been talking about feels like it's on a very large scale. We're measuring things in light years and galaxies. And I was reading today about the new thing about supermasses and looking at black holes on a microscopic level. And I was wondering is there any interplay between the kind of research you're doing and the microscopic level of a black hole?
I can try to answer that. Cameron may want to pitch in. I think what's happening on a microscopic level is very important for the type of things I described. And so I mentioned earlier, it's really hard to simulate black hole accretion. And that's because, so I talked about friction, but I didn't really tell you what that meant in any more detail. And in reality, this friction is various forces acting on these particles that are related to magnetic fields and what we called viscosity, which, like honey is sort of thick. Black hole accretion disks have the same sort of behavior, but we don't understand at all, or not at all, we don't understand very well what produces this viscosity, but it is all at a microscopic scale. And so this is why it's really hard to simulate, because you need to simulate these tiny little scales that are producing the viscosity that generates the friction. It's related to magnetic fields and all these complicated things that we have trouble modeling. But then you also need to simulate things on light year scales, because that's how big these things are in the end. And so there's a very direct interplay that makes it a challenging problem.
Yes, it's very difficult to do this primarily for the reason that Gene says, because you're trying to model very large structures as well as very fine structures. And in simulations, for the most part, you can choose kind of a resolution scale, a resolution element, and maybe you can, let's say the size of your box that of the stuff that you're trying to simulate. Let's say it's a galaxy. Maybe you can have your finest resolution element be 1/1000th or maybe 1/1,000,000th that scale. But what we're talking about for the size structure of a galaxy down to the scale at which the interparticle spacing is like 20 orders of magnitude, and it's very difficult to do in a self-consistent way in the simulations. But one thing that you can do is kind of use higher resolution simulations to parameterize the behavior of things on very small scales and kind of plug that back into the larger scales, so you aren't consistently resolving those very, very fine scales, but you have a pretty good idea of how it's behaving. It's called a subgrid model, because you have a model for the behavior of things below the grid resolution of your simulation. And so this is a lot of the efforts that we're trying to do to model many things in astrophysics, but in particular the accretion physics associated with this. And as was mentioned previously, one of the professors here, Professor Phil Hopkins, recently had a computer model that was able to do a lot of this resolving of the accretion physics, and it showed that one thing in particular that was kind of surprising is that these accretion disks, the stuff that's falling onto the black hole, is very highly magnetized. It has extremely strong magnetic fields, which is probably true and gives us a hint at maybe why some of these weird phenomena are occurring, like flinging out these jets at near the speed of light, these relativistic jets that were talked about. That seems super wonky and weird, right? Well, magnetic fields make you do crazy things. So it holds together self-consistently at that level. But it's definitely an open question and something that a lot of physicists are trying to model and understand. Yeah. Okay. You, and then you, and then you.
Oh, hi. If the black holes keep eating, will the visible matter in the universe less and less in the future?
Yeah, I've actually gotten a question just like this before. Like, if you just put a black hole in a galaxy and wait long enough, what's going to happen to the galaxy? I think if you wait long enough, I don't see a reason black holes wouldn't just keep consuming everything around them. It's going to take a really long time, though, because you have to get lucky enough for every particle of matter to eventually fall into the black hole. And that, as Pranav has sort of talked about, it's hard to get things on this perfect orbit to go into a black hole, and there's not that many black holes. But I think in principle, if you're willing to wait a very, very long time, black holes could just eat everything. I don't see why not.
Yeah, I can add on to this. So if you think eventually every star will die, and black holes take a very long time to die. So right now we live in a universe that has a lot of stars in it, but there are around 100 million stellar mass black holes in our Milky Way. And eventually our universe and every galaxy in our universe will become a graveyard of stellar remnants, many of which will be black holes. And black holes will dominate a certain phase of the universe. You can just call it the black hole era of the universe, where galaxies will just be hierarchical graveyards of black holes. So we're very happy to be at a time where we can see stars.
And in fact, kind of the most probable hypothesis, or the most accepted hypothesis for kind of the end of the universe, is this phase. And then it's something that we haven't really talked about thus far. Black holes, for the most part, just grow and get more massive. But as he alluded, they do lose mass through a process called Hawking radiation, where slowly they radiate away their mass and evaporate, but it takes very, very, very long timescales to do. And that's kind of what we think the end of the universe would be, is that everything gets into black holes, and then the black holes take a very long time to evaporate their radiation around. And then you have this kind of, it's referred to as heat death. It's essentially this kind of bath of photons going in all directions, all roughly at the same temperature. The way I try and think of it is like, imagine you're in a big auditorium and there's a few different fog machines that are pumping out fog. Initially, you have concentrations of fog here and there and here and there, but eventually it kind of fills the entire auditorium or gymnasium or whatever your space is with this kind of uniform bath of fog. That's essentially the radiation that will be expelled by these black holes in the very, very distant future, and then it's a pretty boring place. Depressing, though.
Hi, I loved your talk, by the way. I also loved the book reference at the beginning and how you tied it all into the presentation. So my question specifically is about tidal forces, and specifically how the model accounts for these tidal forces, especially closer to the center of the accretion disk. What kind of mechanics do we see as a result of that?
So I think where the tidal forces come into play more than in the accretion disk, because that's just a bunch of gas particles, and things get pulled into the black hole at different radii, but you don't have any like big solid things like stars that'll get totally shredded by tidal forces. That's when you have to start worrying about tidal forces. If you have like some object that's got a large enough radius that the gravitational pull on each side is very different, but a gas particle is a particle. And so this is why when stars start coming into play, like when there's stars in the accretion disk, or you have a star getting close to a black hole, that's when you start thinking about tidal forces. And so there you can get these things called tidal disruption events, which I sort of mentioned, where stars, as they get close to a black hole, get stretched apart by the tidal forces and shredded into gas, stellar debris that gets fed into the black hole. And this also can happen if there's a star in the accretion disk that's falling into the black hole. It'll get shredded as it gets closer and closer. And this is something we observe. We can see it with telescopes. We watch black holes consuming matter in these transient events called tidal disruption events, which is stars getting shredded by the black holes. And that's most of what my PhD thesis is on. And I should actually give credit for the title of the talk to my friend. I did not come up with that. I'm not that clever.
It seems like the only information that escapes, that's quotation marks to the people who are online, a black hole is mass and rotation. Is there any reason why, or any other information that escapes?
Yeah, that's the fundamental. These are the fundamental properties of the black hole, of any black hole. So, the black holes are somehow the simplest objects in the universe because you don't need to complicate things too much. They have a mass, they rotate. Some people thought at the beginning also of when they were conceptualizing black holes that they may have charge, but we know that astrophysical black holes are not charged because they are neutral. So there is no electricity in the black hole. If you take a black hole that is just sitting there, there is nothing but a massive object. So gravity is dominating there, and it may or may not be rotating. So that's called the no-hair theorem. So that they don't have anything else, and they are you can describe any black hole just using a mass and the rotation. That's it.
But it's interesting you bring this up because there's kind of an ongoing paradox called like the quantum information paradox or quantum information black hole paradox. And it's essentially a mismatch. One of the biggest questions in all of physics today is how to merge gravity and general relativity with quantum mechanics, these two very popular and very accurate portrayals of the behavior of our world around us. Quantum mostly describing things on very small scales, and general relativity mostly describing things on very large scales. But how do we merge those together? But one of the kind of challenges there is that quantum mechanics says that information cannot be lost from any kind of system. So if you throw in a bunch of stars or a bunch of elephants into a black hole, it should, in theory, be extractable what is actually inside of there. But as Elias was just saying, it's very difficult because once stuff goes in, it's roughly disconnected from the rest of our universe, and it's just mass, and you just have mass and you have rotation, and that describes the entire macrostructure of a black hole. So how do you couple these two together? Which wins? Does quantum win? Is there a way to somehow figure out, based on Hawking radiation or something like that, what was inside as it slowly evaporates over time? Would there be a way to pull out the relevant information to figure out what was actually inside? And a black hole that is full of pink elephants versus a black hole that's full of stars, would there be a way to discern that simply by the radiation that comes away from it? Quantum mechanics says yes, but practically we don't yet have a method for doing that. So it's an interesting question that you raise. I had one question from the online audience that I thought would be a good one for us to talk about, because we only have a few minutes left, but we can try and get some more questions here too. And that is, we've talked a lot about the spin with a black hole. It's rotating in a particular way. We've also talked about the accretion disk of material that's going around it and eventually falling in. And then we've also talked about these things usually being, supermassive black holes in particular, sitting in the inside of a galaxy, that galaxies like our own Milky Way tend to have a rotation vector as well. Are these all aligned in their angular momentum, in their rotation, or can they be offset from each other, or what happens there?
Everything could happen, and we're trying to address this, because if we think that some of the material could go from the galaxy to the accretion to the black hole, so these should be connected, or there should be a way of favoring this transport of gas and energy down to the black hole. So the problem is that it's much so simply one may think that everything is co-rotating, and at some point things will adjust with time so that everything is co-rotating, but also these places are also very violent, very alive, everything's happening. And one of the things that were mentioned also is merger. And once you have a merger, so two galaxies, or a big galaxy and a smaller galaxy, or even a tidal disruption event, or anything that is happening close to the central object in the central black hole, so everything will get disrupted and change. So the alignment would change easily. If you wait a long time, things will settle down. It will gain some kind of equilibrium. But what we are seeing now is practically we're seeing snapshots of the universe. So if you see an object, it may be aligned, it may be not aligned. And with some of the summer students here last summer here, we are trying to address the issue if the black hole, so if the accretion disk and the host galaxy are aligned or not. because we don't know what's happening. And in many places, so we see some of the AGN of the active galaxies, they center very bright black holes. Some of them we see that there is some gas that is obscuring the inner part, the torus or the donut that you mentioned before, Cameron. So if we are looking at these donuts, so practically we're looking in a preferred direction, which is kind of edge on. We are looking at the donut, we don't have access. But then you look at the galaxy and you see that the galaxy is facing you. It's a spiral. It's a very beautiful spiral that's facing you. So is this material inside aligned with the disk of the galaxy, or it's misaligned, and why? And that could be one idea of understanding how the black hole evolved, how it grew, because if there is some offset, some misalignment, maybe it's due to some merging or some violent events that happened inside, and that's how they grow. And we're trying to address this, but.
And I can just add that you get some very fun behavior if, for example, the accretion disk is misaligned with the black hole spin. So I once saw these videos of some simulations from some folks at Northwestern who were trying to simulate if you have a black hole that's spinning in one direction, but say an accretion disk forms. Say you have one of these stellar disruption events, right? The tides have shredded a star. That accretion disk may be aligned with the star's orbit, not the black hole spin. But as we were saying, things want to align themselves all together. Everything wants to be aligned. But the accretion disk is misaligned with the black hole spin, and so it'll start precessing to try to line itself up. And that can actually cause the accretion disk to sort of snap at a certain point. You'll see an outer accretion disk that's completely misaligned, an inner accretion disk that's starting to be aligned a little bit more, and even more inner accretion disk that's even more aligned. And then you can have phenomena like if it launches a jet, it might hit a portion of the outer accretion disk that's facing one direction, and the inner accretion disk is doing something completely different. And so this is sort of an active field of research, what that looks like, and if there's any phenomena that you can see in observations from it.
I just want to add, when we talk about the material that's close to the black hole and orbiting it, one way that high energy astronomers try and characterize how the black hole is spinning and whether it's aligned or not is through a concept that you might hear called the innermost stable circular orbit, or ISCO. And the location of where that ISCO is depends on the spin and whether it's aligned or not. So that's something we can observationally do to try and figure this out.
There was an entertaining paper title that came out recently that's Panic at the ISCO, instead of the band Panic at the Disco, which I chuckled at. Notably, on April 1st, there's a number of fake papers that come out through the literature, like joke papers. So last week, there were a bunch of April Fool's papers. I don't think this was, actually Panic at the ISCO, I think was a real paper, but there are a number of kind of like jokey papers because scientists try and make jokes too. There was a question back here.
Does the size or density of an accretion disk affect the rate of Hawking radiation?
It's not usually the accretion disk that impacts the Hawking radiation. For the most part, it's an interaction along the event horizon of the black hole itself, without regard to how much stuff is actively falling in. So I think it's irrelevant with the accretion.
No, it's
disk.
irrelevant. It can happen. I mean, Hawking radiation happens also for dormant black holes. So you expect any black hole to radiate and to evaporate eventually at some point. So it's not really related now.
And there's a question. Here you
So you're talking about the era of black holes, but there's also like supernovas and the birth of stars within them. So would there just be the birth of stars or supernovas that would then be consumed by black holes, or what would that actually look like? Yeah, the distant future. Yeah.
It's just, I think it's after all of the supernovae. So, you have stars. The most massive of those stars will turn into these stellar explosions, leaving behind a core black hole. And then there are other stars like our own sun that won't become a supernova. It won't become a black hole, but it'll still kind of die, so to speak. And that stuff will eventually get merged into existing black holes. I think that's what you were referring to, Pranav, right?
Yeah, at the very end of the day, black holes will be what will remain. Everything will eventually fall into a black hole one way or another. But if you're talking about how supernovas relate to the birth of other stars, I would say Massive stars are the ones that generate a lot of elements before they die, and then the supernova throws that out into the cosmos, and then that eventually gets mixed, and you get new generations of stars that are born with higher metallicity fractions, we call them, because they have more of these heavy elements in them. And then the next generation of massive stars dies, and then it creates even more elements. Basically, if you had just hydrogen and helium, of course, you would never get planets like Earth that have a lot of other elements in them, and you wouldn't get life on planets like Earth. That's why people say we are stardust and stuff like that. And so, you know, if massive stars didn't live and die in violent ways, we would never get the birth of life. But yeah, when we talk about black holes being all that's left, the depressing note I have to end on is that the universe is a lot more optimized for black holes than it is life.
And on that note, we've reached the end of our night. Thank you guys for sticking around. Thank you to our panelists and our speaker. Wonderful presentation, Gene. We'll be back next month, May 2nd, Friday, May 2nd, for a talk all about galactic atmospheres. And I should note our Astronomy on Tap is a week from this coming Monday on April 14th. And I misspoke. It's not going to be about gravitational waves. It's going to be about stellar mergers and the resulting explosions that you see from these these stars colliding with each other, as well as a talk all about what we can learn about the formation of planets from exoplanets' atmospheres. And yeah, I think that's all I got. So have a wonderful weekend. Have a wonderful evening.